All right, so here's our next example. Okay, this is going to be very similar to the last one. We'll go through a little bit quicker this time now that you got the idea. All right, so let's go straight into it. It says determine the independent and dependent variables. We can say, well, our independent variable is the distance from the center, and our dependent variable is the acceleration of gravity. All right, so we can go ahead and do that. Okay, and we know that because we are measuring the acceleration of gravity at each distance, at each point, right? And so we're finding that distance from the center, measuring gravity there. The acceleration of gravity depends on the distance from the center. All right, we can go ahead and label the graph, put the data points on. I'll do that. Pause the video if you need to, but go ahead and do that. I think you're probably okay with that. All right, so you can see I got my data points on here, labeled the axes. On the y-axis, I thought about going by 2s, but I couldn't quite get up to 10 over there if I went by 2s, so I ended up going by 1s, and that's fine. It still takes up a little more than half of the graph, and that's probably the best we're going to get out of this. If I had a choice, I'd probably go back and use my own graph paper if I had something like this, just so I could stretch it out a little bit more. But, I mean, you can look at this right now. You can see that if we put in a line here, I'm trying to make it one nice smooth line. You might be tempted initially to put a straight line in there, because a straight line the data points would all be close, but you would notice that on the ends, the points are a little bit above the line, and in the middle, the points are a little bit below the line. And so that's a pretty good indication when on the ends, all the points are on one side of the line, and in the middle, all the points are on the other side of the line. It's usually a good indicator that the line really should be curving. Now, because this is just the left-hand side, we're probably not going to say this is a quadratic. We're probably going to say it's either an inverse or an inverse squared. Now, I already know what it is. It's an inverse squared. But looking at it, you may say, it looks like an inverse. And so you could try to do inverse. All right, you could try to go into the x values and do 1 over 6, 1 over 7, 1 over 8, and so on and so forth. And if you did that, you would end up getting a new graph. The new graph would not be linear, and so you would know that it is not inverse. Okay, what we're going to do instead is we're going to actually do inverse squared. So we're going to do 1 over 6 squared, 1 over 7 squared, 1 over 8 squared, not 8 to the 8th, 1 over 9 squared, 1 over 10 squared, 1 over 11 squared, and 1 over 12 squared. So what I'm going to do real quick is I'm going to punch these into my calculator and get some decimal values. All right, so we got some decimal values here. This will be a little bit easier to put in. When I put it onto my x-axis later, I'm probably going to use some weird units, right? I already know that already it's 1 over megameters squared, right? Because that's what I just did. I just did the inverse squared of each of those megameters. What I'm also going to do is I'm also going to go times 10 to the negative third. And what that'll allow me to do is move the decimal over 3 places. So I'll have 27.8, 20.4, 15.6. The last number will be 6.9. So it'll be a little bit easier to work with when I put it on the graph. All right? And so that's what we're going to do right now. So here we go. Move it on up. We'll see if we can throw this graph on here. On the x-axis, I'm going to use these units. Okay? So this is now 1 over distance squared, which is going to be in 1 over megameters squared times 10 to the negative third. And so I'm going to start over here with 1, 2, sorry, that should be 0. 1, 2, 3, 4, 5, 6, up to 12. Similar as before. Add 6 every time. 24, 30, 36. That should give me plenty of space already to be able to fit all the way up to that 27.8. On the y-axis, again, that doesn't need to change. So I just go 1, 2, 3, 4, 5, all the way up. 10. And I'll put on my label there and go ahead and put the points on. And let's see what it looks like.
And look at that. We get a nice, lovely straight line. Man, that is amazing. Look at that lovely straight line that we've got there. Actually, I should use a straight edge for this, shouldn't I? We're going to go ahead and make the nicest straight line that we can make. Oh, well, so much for my nice straight line. Shouldn't use a post-it note, I guess. Anyway, you got my straight line. Look at that. That is just, I don't even know what to say. That's just a beautiful straight line. All right, we should be able to write an equation now, right? This is a straight line, which means it follows the equation y equals mx plus b. The b is going to be 0. I can see that it crosses 0 right there. Okay. And then I need a slope, so I can get a slope from a couple of different points. So I'm going to use 0, 0, and another point. It looks like it goes through this point right here pretty well, which I'm going to say right there, that point right there is 28, 10. And so that means I have a slope of 28 over 10, which is 14 over 5. And so in other words, we have y equals 14 over 5 times x plus 0. But we're going to put our correct variables back in there. So what is y? Well, the y-axis was the acceleration of gravity. I didn't write it here, sorry. I did exactly the same. The y-axis didn't change. So y is the acceleration. So we put acceleration in for the y equals 14 over 5 times x. But remember, x was 1 over the distance squared. I'm going to just use a capital D for my distance there, the distance from the center of the earth, and then plus the 0. And so this right here is a nice equation that I can put any distance from the center of the earth, any independent variable in there, and I would get the dependent variable, the acceleration for y. Now, some of you may ask, well, why can't I just use this graph up here? Can't I just use my fancy smancy calculator or computer to give me a best fit line there? Yeah, you could, but there's a couple of advantages to the linearization process. I'm going to finish with this. The advantages to this, number one, you can basically do this almost without a calculator, right? Maybe you need to do some of those divisions with the squareds, but the previous question we did without a calculator, right? You could linearize this and you could come up with the equation without any type of calculator. You can do it by hand. You are understanding this linearization process. You're understanding how the variables are related by recognizing that it's an inverse squared relationship. The other thing that's nice is we can actually calculate a slope here, right? In this equation, we can calculate a slope. And if I had an equation and I knew what the relationship was, if I had a formula because I understand the situation, and I say, I believe that the situation should be modeled by this equation, that slope could actually mean something. And that's what we're going to see in the next video, where I present some questions that are a little bit more AP-like in nature, is you'll be able to see how that slope actually means something, and we actually get information from it, all right? Which this would be a little bit more difficult because of the nature of the equation. Can you still do it? Yeah, but it's a little bit harder mathematically, and we do need a lot more assistance from some type of calculation device. So anyway, that's what we got right there. I hope that was helpful, and I'll see you guys later.